All right, lesson 13C. So let's look at inequalities involving exponential and logarithmic expressions in this last section here on lesson 2.13. All right, if our b is greater than 1, properties of exponential inequalities. If our base is greater than 1, then the exponential function y equals b to the x is increasing for all of x. This means that b raised to the x is less than b raised to the y if and only if x is less than y. But number 2 tells us if our base is between 0 and 1, then the exponential function y equals b to the x is decreasing for all of x. This means that if b to the x is greater than b to the y, that's if and only if x is less than y. So the big takeaway here is if your base is greater than 1, then your signs here will stay the same. If your base is between 0 and 1, your inequality sign here will switch because it's decreasing instead of increasing. So same inequality if its base is greater than 1, change or switch the inequality if it's between 0 and 1. All right, so look at example 16. It says, find the solution set of the inequality, check for extraneous solutions, and verify your answer with a graphing utility. All right, so we have 5 to the x is greater than 125 raised to the x plus 6. So just like it had an equal sign, we can get like bases, so let's do that. So we got 5 to the x is greater than 125 is 5 to the third to the x plus 6. And so we get 5 to the x is greater than 5 to the, remember you multiply, so distribute, so the 3x plus 18. My base is 5, which is greater than 1. So when I ignore them, that means my inequality sign, though, is going to stay the same. And so we're just going to solve this inequality. So we get x is greater than 3x plus 18. Subtract the 3x. Negative 2x is greater than 18. Divide by the negative 2. And we know x is less than negative 9. Don't forget, when you divide by a negative number, you have to switch the sign. All right, so we believe our solution then is going to be from negative infinity to negative 9, not included. Now, if I want to check this on my calculator, I'm just going to type in this piece. Let me change colors. I'm going to type in this piece here. I'm going to put the left side in y1, the right side in y2. All right, so when I go to graph y equals x, and I go to graph the y equals 3x plus 18, so I'm going to label this is what I put in y1, this is what I put in my y2. I can see that I want y1 to be greater than, remember greater than means above. It is above right here. Let me change colors again. Y1 is greater than the other one right there. So I need to find that intersection, which is going to be at that negative 9. And I know that then from negative 9 all the way over to negative infinity is where it's going to be greater than. But remember, we always write it in numerical order, so negative infinity to negative 9. All right, look at B. So B, we can get like bases because we know 27 has a base of 3. So this is going to be 1/3 to the 2x plus 9. It's less than or equal to 1 over 27 is 1/3 raised to the 3 raised to the what gives me 27? A 3. And that's all raised to the x minus 3. So I end up with 1/3 raised to the 2x plus 9 is less than or equal to 1/3 raised to the 3x minus 9. And my bases are the same, so I can ignore them. So I have 2x plus 9, but my base is 1/3. My base is between 0 and 1, so I'm going to flip that inequality sign there. And then I have my 3x minus 9. And so that's the inequality that I'm going to solve. So 2x plus 9 is greater than or equal to 3x minus 9. Subtract the 3x. Subtract the 9. So I end up with negative x is greater than or equal to negative 18. Divide by negative 1. So x is less than or equal to 18. And so we know if it's less than, it's going to go to negative infinity all the way to 18. That is included because it has that equal to. Now, to verify this algebraically, I'm going to graph my inequality here. So I'm going to put 2x plus 9 in y1, 3x minus 9 in y2. So when I graph y1, and then I'm going to graph y2, I want to know when what I put in y1 is greater than y2. So I'm looking for where it's above. So that's going to be all of that area there. Y1 is above right here. So I find the intersection, which is going to be at 18. And I know it's from 18 all the way to the left, so all the way to negative infinity. So negative infinity to 18. 18 is included because my inequality symbol has an equal to. All right, properties of logarithmic inequalities here. So if your base is greater than 1, if you have log base b of x greater than log base b of y, that's if x is greater than y. That's also true for less than or equal to, or greater than or equal to. All right, so if my base is greater than 1 on logarithms, it's the same as it was with exponentials, okay? The inequality sign will stay the same. All right, if my base is between 0 and 1, number 2 says if my base is between 0 and 1, then log base b of x is less than log base b of y, then x has to be greater than y, and that's also true for less than or equal to. And if my base is between 0 and 1, then log base b of x is greater than log base b of y, then x is less than y, also true for greater than or equal to. All right, so what we're seeing here is that they're going to change. So it's the same rules. If the base is greater than 1, my inequality sign will stay the same. If my base is between 0 and 1, then we're going to switch the inequality sign. All right, so let's look at 17. It says find the solution set of the inequality. Check for extraneous solutions. Verify your answer with the graphing utility. All right, so I see here I have this inequality, but first I don't have a log on both, just a log on both sides. On the right side there I have that 2 log. So I need to move that 2. Remember, it can become the exponent. So this is log base 2 of 9 is greater than log base 2 of x squared. All right, since my log base 2's are the same, we can get rid of them. And so we know 9, but now I have a base of 2, which is greater than 1. So the inequality sign is going to stay the same. The x squared, take the square root, and we get plus or minus 3 is greater than x. Now you have to be careful here because remember we're dealing with logs, and with logs we can't take the log of a negative number. So you got to put this inequality together with what its domain can be. So on this one, the log base 2 of 9, it's just a number, okay? So don't worry about it. It's that log base 2 of x we have to worry about. So for log base 2 of x, we know its domain is going to be from 0 to infinity. Okay, it's greater than 0. Well, let me write it like that. So we know that x has to be greater than 0. This told us that our x was also going to be, I'm going to flip it over, less than positive or negative 3. So I'm going to think about this on a number line. So here's my 0, my negative 3, and my positive 3. All right, the first one says x has to be greater than 0, so it's going to be all those numbers. Then I have x is less than 3, which is all of these, and I have x is less than negative 3, which is all of these. All right, so it has to make the domain and the other part true. So we can see the only place where any of the overlapping between the domain and anything else is from 0 to 3. And so that is going to be our solution. So from 0 to 3, not included because the 3 wasn't included in the inequality. All right, let's look at B. We have log base 2 of 2x plus 1 is less than or equal to 3. So this time I only have a single log, so we're going to set it up in exponential. Now my log is on the left, so that piece is going to stay on the left. We're used to doing 2 to the third equals what, the 2x plus 1, but because the log is on the left, keep the 2x plus 1 on the left. So we're going to have our 2 to the third and equals the 2x plus 1. But for inequality's sake, the 2x plus 1 has to stay on the left side because that's where its log is at. All right, my base is 2, which is greater than 1. But this one we can go ahead and keep solving. So we got 2x plus 1 is less than or equal to 8. Subtract the 1. 2x is less than or equal to 7. Divide by the 2. And so we get x is less than or equal to 3.5, or 7/2. All right, but you also got to remember, we got to think about the domain. So I have this log right here. So we know that log base 2 of 2x plus 1 tells us that the 2x plus 1 has to be greater than 0. So that means 2x has to be greater than -1, and x has to be greater than -1/2. But we also know we got as our answer that x has to be less than or equal to 3.5. So again, I'm just going to kind of use a number line here. So here's my -1/2. Here's my 3.5. The greater than -1/2 is this away. Less than 3.5 is this away. They overlap right here in the middle. So I know it's going to be from -1/2 to 3.5. The 3.5 is included, but the -1/2 is not. And so there is our solution. All right, C. This time we have a log with a log on the other side. And so we're able to just go ahead and ignore the logs, but look at your base. This time your base is between 0 and 1. So remember, that means your inequality sign is going to switch, okay? So we have that 2x minus 3 is going to be less than or equal to the x plus 5. And so then we can just solve. And so we get x is less than or equal to 8. Again, think about your domain. This time we have 2 logs, so we got to think about both of their domains, okay? The first one, the 2x minus 3, has to be greater than 0. So 2x is greater than 3, which means x is greater than 1.5. The other log has an x plus 5 has to be greater than 0, so x has to be greater than -5. All right, and then we still have our x is less than or equal to -8. So when I do this, I have what? -5, 1.5, and 8. So I know it's going to have to be greater than 1.5. It's got to be greater than -5. So I can already see I'm looking at this piece right now because this part doesn't make the first one true. And then less than 8. So I can see their overlap is right here between these two numbers. So it's going to be from 1.5 to 8. 1.5 is not included, but the 8 is. And so there is our solution. And that is it for lesson 13.